All right, so let's look at protein then. For 4.9, it's really an extension of amide. Amide is a building block, and then if you extend it by making like bigger polymer, macromolecules, you're making proteins. And you will also look at breaking protein as well in here. Okay. As usual, what you need to be able to do, you need to be able to determine whether or not a compound is an amino acid given its structural formula. It sounds kind of familiar. Draw the structural formula of the product formed when an amino acid self-ionizes. We'll look at that. We'll look at Twitter ion or something like that. Identify the amide group and deduce the structural formulae of the monomers given the structural formula of a section of a protein. It's a very common question in the exam because protein can incorporate a lot of different types of organic functional groups. Okay, so you might be getting a context where you're given a section of protein. Again, it's application of everything else that you have learned so far. Okay, and you need to be able to tell what group is what. Write the general formula of amino acids and recognize their structural formula. Last 3. Identify where hydrogen bonding can occur between protein chains or between the chain and water, given the structural formula of a section of the chain. Second last, explain why the biological function of a protein, for example, like an enzyme, is altered if its spatial arrangement is altered. Finally, explain why proteins are sensitive to changes in pH and temperature. So in another word, cooking or curing meat or prawns or whatever. Okay. Now, amino acids. When you look at proteins, the building blocks are amino acids. Yeah, and amino acids have got amino group, amine that is, acid, so that's carboxylic acid. So it needs to have both functional groups. So on one end or within somewhere in the chain, it should have amine group, and the carboxylic acid should also appear. And R, hopefully represents the side chain, any alkyl group, and could be any length. And depending on the length or what's attached to, the function of amino acid changes. Yeah, the TCAG that you hear in DNA, they all have got different groups attached to, but it has amine group and carboxylic acid group on its ends. Yeah? And proteins are products of condensation reactions between amino acids. Again, it's a very hard thing to do in the lab, but it can happen readily, in nature, in our stomach, or when apples are being made into apples. It's a wonder of nature, isn't it? Amino acids contain both an acidic group and a basic group, COH and NH2 respectively. Thus, they have both the ability to donate and accept protons. Now, when there is proton from outside, acid, that can be protonating a basic group, the amine group. But because there are acid and base, it can do self-ionization. Okay, so within the same amino acid, the proton from acid N can come to amino group, amine group, sorry. In this process, amino acid requires positive and negative charge in both ends, and you will get what's called Twitter ion. Can you try drawing what you would get if this amino acid self-ionizes? So remember how amine accepts proton. So if you are drawing NH3 on one end, H yeah. So that's where you start with. This acid group can donate proton, so negative charge can be left there, and that hydrogen can be transferred to here, because nitrogen has lone pair of electron, non-bonding electron pair. Important thing, again, is to add the positive sign on nitrogen. Yeah, so that's Twitter ion that you can get. I'm not actually sure if I'm saying that word right. Twitter ion. Twitter ion. Anyway, moving on. So amino group is one amino acid, can react with carboxylic acid group is another amino acid to form amide group. Okay, and proteins are large molecules that contain many amino acid monomer units joined together. Thus, proteins are also referred as, underline them or highlight them, polypeptides or polyamides. Polypeptides is probably what you hear in bio a fair bit. Polyamides, well, same thing, no? So if you look at this slide, you can see where the monomer unit is. It's a visual representation of what it was saying on the previous slide. So monomer unit starts with NH and ends with CO double bond there. Yeah. So it's repeating itself. Whereas peptide link, which is working as like connection between amine group and carboxylic acid group, that was originally there. It's amide, really. Okay, so peptide links are really amides. Okay, so end of one amino acid to another amino acid group, they join together to make peptide link or bond. All right, and happens readily in organic living organisms. Again, it's very hard to do in practical setup. Hydrogen bonding. Now, proteins can form its shape and keep its shape as it is due to hydrogen bonding. Or you could also have other bonding, like dipole-dipole type of thing, or even covalent bond using sulfur as a chain. Okay, but for say DNA to be able to replicate itself, to be able to uncoil and coil back again, it actually needs to have a bit of flexibility. And hydrogen bonding is not actually bonding, is it? It's interaction. So it's strong enough to keep the shape, but it allows the say DNA to uncoil, replicate, go back to double helix again, yeah, because of the hydrogen bonding. So as well as polar amide links, side chains of amino acids may also contain polar groups. Anything polar can have polarity and a bit of rigidness within the shape of protein. So NH2, that can cause hydrogen bonding. CO bond, carbonyl groups or carboxylic acid group, and hydroxyl group as well. These polar groups allow protein to form hydrogen bonds between sections of the same protein chain, between separate chains, and also between protein and water. So for example, if you had a chain of protein and there was water, it could be interacting here and there, hydrogen bonding being formed. Okay. again, quite popular question for you to be able to draw the interaction between one molecule and water, right? Or one protein chain to another protein chain. Structure of protein. It's something that determines its function. Think of cooking egg or cooking meat. Okay? Cooking egg. If you don't cook and if it was fertilized, it can be new life. The chicks can just hatch from the egg. But if you cook the egg, even if it was fertilized, would it become a chick? No. So all the function that the protein had, the protein is destined to be, I don't know, part of the heart or part of the head or wings or whatever, they're all gone. Yeah, because you cooked them. All right. Meat is the same. If you cook steak, it's very hard to uncook the meat. Yeah, and let the meat gain original function. Yeah. So that's to do with you modifying the structure of the protein somehow. Okay? And when you say structure, chemically speaking, we are talking about rearranging atoms. Okay? The biological function of protein is directly related to structure, particularly its 3D structure. This is because the structure of protein determines its shape and thus the way in which it interacts with other molecules. Now, what did I say about shape? How do proteins keep its shape? Hydrogen bonding, interaction, yeah, between a chain and chain or chain with something else outside. Yeah, good. So that's what we need to think about. Structure of protein was, again, this may be new, this may not be new to you, but primary structure we are talking about is just a line, the thin, string, really. I thought I had some string or yarn bubbles. Yeah, mine, it's gone. All right, primary structure is the thread, okay? It's long string, that's it. Amino acids are connected between using peptide link, and that's our primary structure. And if that structure started coiling up, that will be called secondary structure. Most common structure for alpha helix and beta sheets. One protein chain may have multiple sections arranged into different secondary structures. So what we are saying is, if you have a string, that can be in different sort of shape fairly easily. Okay, so uncoiled version is primary, and coiled version of the string is secondary. And that's what it looks like. Should look familiar. Some sort of helix. So if you had double helix, that'll be DNA, wouldn't it? All right. Also, if you have a string and kind of go up and down, or zigzag sort of way, you can have almost like sheet sort of structure, okay? Because they're interacting and they're sort of connected. The lines are connected to each other, so it will act as like sheet, okay? Tertiary structure will be a combination of those string sort of shape, coiled up shape, and coil of sheet or sheet only. So what you can see there on the diagram there, alpha helix is a coil of sheet, I reckon, and a beta plated sheet is, well, this thing sheet that has a wave of the string. Quaternary structure would be connecting all those 3D shapes together. So things like hemoglobin at the end there, at the bottom in that slide, that will be quaternary structure, complex protein molecules, which has got, sorry? Yeah. So yeah, you would start with primary one, a GTAC type of thing, that can make coil sheets, and if you put the sheets together, you can make one part of big protein. And hemoglobin here has got 4 different big parts to it, yeah, type of thing. Ordering protein structures usually fairly easy. Again, what happens if you heat any sort of atoms? What do atoms do? They move faster. Good. More energy means they can move faster. And then let's put that into the context of protein. So some atoms are, interacting. They are pulling each other to start with. But each atom starts getting more heat or energy. What's going to happen? They'll break off a little bit. So temperature affects it fairly easily. Hydrogen bond is also very easily altered by pH as well. So like cooking egg, curing salmon, cooking prawn with lemon juice. Yeah, they're all to do with you changing the structure of protein by altering either heat or pH level.
You can cook something with pH.
Yeah. That's what like pickles kind of do, or cured salmon, or sushi was actually invented because that was putting into fermented rice, a very sour fermented rice. That was the first thing they did to preserve fish. Yeah, rice wasn't eaten originally. They were just wanting to, preserve fish only with sourness. But they found that eating the sour rice with the sour fish was actually very nice. So that was the start of sushi.
History
All right, we'll talk about tardigrades later on. All right, I'll see you later.